In today's video, we are going to be looking at increasing versus decreasing. So before we even get into increasing versus decreasing, we first have to introduce two results that are needed for this study. Those results are Rolle's theorem and the mean value theorem. We will then review the definitions of increasing and decreasing, and then jump into developing a test for increasing and decreasing using the first derivative. And we will also state what's known as the first derivative test, which is a way of using the first derivative to test whether a point results in a relative maximum or a relative minimum. So we begin by introducing what's known as Rolle's theorem. And Rolle's theorem states, let f be a continuous function over the closed interval a to b. And it is differentiable over the open interval a to b. Right? So it doesn't need to be differentiable at the endpoints, such that f of a is equal to f of b. So the function value is the same at the endpoints. Then there exists at least one c in the open interval a to b such that f prime of c is equal to 0. Right? In other words, the function is going to have to turn at least once. Right? So now we prove this. And what we're going to do is we're going to let k be that value, that f of a and f of b both equal. And there are three cases that we have to consider. First, suppose that f of x is constant over the entire interval. That is, f of x equals k for all x in the interval a to b. Well then, obviously, f prime of x is equal to 0 for all x in a to b, right? Derivative of a constant is always 0. So we're done. Second case. Suppose that there exists an x in the open interval a to b such that f of x is greater than k. Now, since f is continuous over the closed interval a to b, it has an absolute maximum by the mean value theorem. I'm sorry, by the extreme value theorem that was studied in the previous video in this series. Furthermore, this value is greater than k. Therefore, it does not occur at the endpoints, right? So this means that the absolute max does not occur at the endpoints. This means that it has to occur at an interior point. Call it C. Now, f of c is a maximum, so f prime of c has to equal 0 by Fermat's theorem. Again, studied in the previous video in this series. Well, we found the point then. We found the c such that f prime of c is 0. Finally, suppose there exists an x in AB such that f of x is less than k. Well, this is analogous. To the case we just proved. Just replace absolute max with absolute min, and the proof is identical, so we're done. That was all three cases, and we found a point such that f prime of c equals 0 in all three cases, so the proof is complete. Now we will use Rolle's theorem to establish another important result in mathematics known as the mean value theorem, or the MVT. So the mean value theorem states, let f be continuous over the closed interval a to b, and differentiable over the open interval a to b. Then there exists at least one point C in a to b such that f prime of c is f of b minus f of a over b minus a. Right, that is, f prime of c is the average value of f over the interval b to a. Right. So we shall prove this. What we do is consider the line that connects the points A, f of a, and B, f of b. Now, since the slope of this line is f of b minus f of a over b minus a, and the line passes through a f of a, the equation of this line is y is equal to f of b minus f of a over b minus a times x minus a, then plus f of a. What we do now is we let g of x denote the vertical distance between the point x f of x and the point xy on that line. In other words, what we have is g of x is equal to f of x minus the quantity f of b minus f of a over b minus a times x minus a plus f of a. Now, these two graphs are going to intersect at x equals a and x equals b. Right, so since the graph of f intersects the secant line, right, because that's exactly the line that we created, at x equals a and x equals b, we have that g of a is equal to 0, which equals g of b. Right, so g at the endpoints are equal. What we're trying to do is establish that g of x satisfies Rolle's theorem. Since f is differentiable, over the interval a to b, so is g. Furthermore, since f is continuous over the closed interval a to b, then so is g. Right? Because g is just difference of two continuous functions, f of x and a line, which is continuous. Same thing as differential, right? And remember, the difference of continuous functions is continuous. The difference of differentiable functions is also differentiable. So we've now established that g of x satisfies the conditions for Rolle's theorem. This means there exists a point C in the open interval a to b such that g prime of C is equal to 0. On the other hand, if we actually take the derivative of g, right, we're going to be left with f prime of x minus, now the derivative of this, well, this is a constant, so derivative of x minus a is just 1. And f of a is also constant, so that derivative is 0. So this just becomes minus f of b minus f of a all over b minus a. What we have to have then is f prime of x minus f of b minus, we have to have f prime of c minus f of b minus f of a over b minus a equal to 0. And we can solve for f prime of c to get f prime of c is equal to f of b minus f of a all over b minus a, which is the result we wanted. And so the result is established. The proof is complete. If we now go ahead and take a look at a function. Let's just say we'll do something like this. That should satisfy our purposes, right? So remember, increasing means that as we move left to right, the values of the function are increasing. Right, so they're getting larger. As we move from left to right, decreasing means that those values are getting smaller. If we look at tangent lines, so we'll have one there, right? We'll have a tangent line here. We'll have a tangent line here. What you should notice is that the slopes of these tangent lines are getting larger. I'm sorry, that's not what I wanted to say. The slopes of these tangent lines are all positive. That's what I wanted. Slopes are positive. But the slope of a tangent line is the derivative. So we have f prime of x is greater than 0. On the other side, if we draw the tangent lines, you should notice, right, that all of the slopes are negative. In other words, f prime of x is less than 0. This observation is now formally stated as our test for increasing, decreasing. So we say let f be continuous over the closed interval a to b and differentiable over the open interval a to b. Number 1, if f prime of x is greater than 0 for all x in the open interval a to b, then f is increasing over that interval. Likewise, if f prime of x is less than 0 for all x in that interval a to b, then f is decreasing over a to b. Now, in order to actually prove that this result is true, we will make use of the mean value theorem. We were only going to consider the proof of the first part. The proof of the second part is similar and so is left to the viewer. Suppose that f is not increasing on I. Then there would exist a and b in I such that A is less than B, but f of A is greater than or equal to f of B. Now, since f is differentiable on I, the mean value theorem says that we must have a value C in A to B such that f prime of C is equal to f of B minus f of A over B minus A. Now, f of B minus f of A would be less than or equal to 0 since f of B is greater than, f of A is greater than or equal to f of B. Also, B minus A must be just strictly larger than 0. This tells us that f prime of C is less than or equal to 0. However, this is a contradiction. Right, so this contradicts the fact that f prime of x is larger than 0 for all x in the interval I. So the original assumption must be incorrect, and our assumption was that f is not increasing. Therefore, we must have that f is increasing over I. And again, the proof of the second part of that test, the decreasing part, is similar. We're now making another observation that involves increasing and decreasing. Let's consider this function here. Right, well, from our discussion in the previous video, we know that these points will be relative max. And we know that these 2 points will be relative minima. But observe what's happening. Right, to the left of the max, we are increasing. Then to the right, we are decreasing in both cases. So this would seem that f prime goes from larger than 0 to less than 0. If we look at the minima, to the left it is decreasing, and then to the right it is increasing. So f prime of x will go from less than 0 to greater than 0 at the minimum. We will now state this observation without proof, and this is known as the first derivative test. Suppose that f is a continuous function over an interval I, containing a critical point C, and we let f be differentiable over the same interval. If f prime changes sign from positive to negative at x equals c, then f of c is a relative max. Two, if f prime changes sign from negative to positive at x equals c, then f of c is a relative minimum. Number three, if f prime does not change sign at x equals c, then f of c is neither a relative max nor a relative min. We will once again consider two examples. For our first example, let's look at the function f of x equals x cubed minus 3x squared minus 9x minus 1. We wish to determine where this is increasing, where it's decreasing, and then determine the extrema. Right, well, the first thing we have to do is find its derivative. 3x squared minus 6x minus 9. So we can find critical points. Well, f prime is defined everywhere, so just set it equal to 0. We can divide by 3 to get x squared minus 2x minus 3 is equal to 0, which can factor. X plus 1 times x minus 3. Right, so we get two critical numbers, x equals negative 1 and x equals positive 3. What we now do is create a sign chart. For f prime. Right, what a sign chart is we just look at the sign of f prime over test intervals. To determine the test intervals, we take the domain of f, which is all real numbers, and split it up at the critical points. So the first one will be minus infinity to minus 1, then we'll go minus 1 to 3, and then finally 3 to infinity. Pick a value from each test interval, plug it into f prime to determine the sign. If we take negative 2 and plug it into f prime, we will get a positive value. If we take 0 and plug it in, we will get a negative value. If we take, let's say, 5 and plug it in, we will get a positive value. So we are increasing over negative infinity to negative 1, unioned with 3 to infinity. We are decreasing over negative 1 to 3. We switch from positive to negative at -1, so that is a relative maximum. Plug -1 back into the function, we'll get 4. We switch from negative to positive at 3, so that is a relative min. And f of 3 winds up being -28. So we've now completely analyzed the first derivative. And one last example. We look at the function f of x equals x to the third, should say 1/3, minus x to the 5/3. So again, take the derivative. We'll have 1/3 x to the minus 2/3 minus 5/3 x to the 2/3. This is 1 over 3x to the third minus 5x to the 2/3 over 3. Simplifying this, we get 1 minus 5x to the 4/3 all over x to the 1/3 power. My apologies. This should have been 1 over 3x to the 2/3. Yes, indeed. There we go. Now, notice that f prime of 0 is undefined, and 0 happens to be in the domain. Setting f prime of x equal to 0, what we'll get is 1 minus 5x to the 4/3 is equal to 0, which means that 1/5 would be equal x to the 4/3. If we cube everything, we get x to the 4th is 1 over 125. So x is plus or minus the 4th root of 1 over 125. I forgot 3 down there. So we have 3 critical numbers. Again, we need to divide our domain up. We'll go minus infinity to negative 4th root 1 over 125. We'll then go from that to 0. We'll go from 0 to the 4th root of 1 over 125. And finally, we'll go from the 4th root of 1 over 125 to infinity. If we take -1 in that first interval, plug it into the derivative, we get positive. If we pick a value between -4th root 125 and 0, we get positive. This will be positive and this will be negative. I'll leave you to verify that. So we are increasing over -4th root 1 over 125 to 0, unioned with 0 to the 4th root 1 over 125. we are decreasing over negative infinity to negative fourth root of 1 over 125. And fourth root of 125 to infinity. Relative max, right? We switch from positive to negative at the fourth root of 1 over 125. Again, I'll leave you to plug that in, but you'll get 4 times the fourth root of 125 over 5. I'm sorry, over 25. For the relative min, we switch from minus to positive at negative fourth root, 1 over 125. So if we plug that back into the function, you'll get negative 4 times the fourth root of 125 all over 25. And that concludes this video on increasing and decreasing functions. So essentially we analyzed the first derivative. The next video in this series will look at the second derivative. So we'll analyze the second derivative function, and this will help us to determine the concavity of the function. So I will see you all in the next video.